Okay, so to lead us off in our next session, which is the coastal ocean interaction with the open ocean, we have Mike Cosrow from OSU, and he's going to be talking about dynamics from basically Oregon northwards. And then following him is Uwe Sen from Scripps, who's going to be talking basically California and south. So that's kind of how we divided this up. And then when we have audience participation, you guys are doing a great job. If it's your first time speaking, why not introduce yourself, like I never did. But anyways, this morning, don't follow my act. But let's get to know each other a little bit better that way. So, all right, Mike, take it away.
I want to start off with something that I had toward the end, which is something of a punchline, but it came up in the discussion just before. These are sea surface temperature anomaly plots for 1 year, month by month, and show the development of the blob, which we've all seen. I just do it for a reminder. Come back to those. Come on. I think there's some good news here, at least potentially. Going back and looking over some of the older sea surface temperature anomaly maps that are held at the NVS site, this is for 8 months or so, starting in May of 2011. And I think what you can see is the development of something that looks familiar to us. So that's 6 months. Here's another 4 months. And this is an alternative case of a warm anomaly in the middle of the North Pacific. There's another case here from the winter of 2004 to 2005, where a blob of warm water develops and, and undergoes significant changes. The reason I think this is good news is because we have some hypotheses, but it's very hard to figure out what's going on with a single case. We don't know if our force balances are fortuitous or repeatable. If these are analogs for the case that we have, although not as strong, they provide an opportunity to test out some hypotheses like the ones we've heard this morning. Okay. Another thing that I wanted to point out having to do with coastal versus open ocean, we've talked about the importance of the upwelling downwelling cycle and whether that serves to modulate the onshore offshore position of warm water. I've gone to the sort of and the question came up last time about the Bakken indices. What I've done is I've taken the Bakken indices that are published by PFEG and sort of reproduced their plots, but strung 3 years together from 2013 to 2016. And the black line is the daily value of the upwelling index. When it's positive, there's strong upwelling at this particular model location, and when it's negative, it's downwelling. And the red line is the seasonal cycle that I fit to it. And so what you can see is that, and the gray lines are the plus or minus a standard deviation. So I think what you can see is even at 51 north, pretty far north, the winds are anomalously strongly upwelling, anomalously weakly strong downwelling through the fall and winter of 2013, 2014. And same thing, fall and winter of 2014, 2015. Richard also alluded to that. But now let's look at other locations along the coast. So this is at 51 north. This is 3 degrees further south. And for that same period, we again have anomalously upwelling favorable or resisting downwelling. 3 degrees further south, down around Newport's latitude, the effect is particularly strong. But now things start to change as we come further south. The anomaly is weaker at the Oregon-California border. By the time we reach Point Arena, it's largely abated, and by the time we get to Monterey, we're back on the seasonal cycle again. So the onshore-offshore cycle of forcing is strongly latitude dependent. There we are down near San Diego and all the way down to 30 north. Those are the two most important pieces that I wanted to show you from things that I'd tried to develop. In order to understand the temperature budget, in order to understand the heating, we need to understand the heat flux and its divergence, so the advection. We need to understand diffusion processes, both vertical and horizontal, and we need to understand the forcing. And we should need to try to isolate all those different processes. Complicated job. This is a figure that Ted Strube contributed, having to do with large-scale patterns of sea level and sea level rise. The figure on the right is the global sea level rise, the trend. So how many millimeters per year over a 10-year, 20-year period are we seeing for sea level rise? And it's up around 5 or higher millimeters per year in the Western Pacific, but all in the Eastern Pacific, the number is much lower. And the question is, why is there a difference between the two if the sea level rise has been minimized along the West Coast due to some large-scale circulation with long-term timescales? The PDO is a suggestion that's offered. Then what happens when that circulation revises itself and either reverses or relaxes? The suggestion may be that this sea level rise pattern adjusts dramatically and we get sudden sea level rise along the US West Coast, which will be a significant impact. And then one other thing, let's see where. This is, so one of the things we suffer from is a lack of information on how deep this process, how deep the blob is and how that varies with space. I haven't looked at the Argo data. That's one of the obvious ways to get at a problem like this. But, and nobody's talked about it yet. I think that's a great project for some grad student to get into. But we do have models, and the models are showing us some interesting things about stratification. Obviously, the stronger the stratification, the more resistant things are to wind mixing, and so the greater increase in a temperature you'll get for a given solar heat input. Alex, did you want to go through some of the details on this?
Okay, so what we have is this model, which is like 2 kilometer resolution, and now we have like 6-year simulation without any data simulation, just like making sure that we can provide best boundary conditions, initial conditions. It's a ROM simulation, and we would like to, basically we have run from 2009 through end of 2014 now. We would like to kind of use that solution to understand some of the issues that have been brought here in the workshop, including subsurface stratification and fluxes, vertical versus horizontal fluxes. So basically, kind of show like, well, one more message I want to convey here is that this is a big model, and we would very much like to see actually other people dice and slice that model and let us do something else. So if anybody is interested in helping us analyzing those models, we'll ship you fields next day. How good are they? Well, I mentioned that we have a 6-year continuous simulation, but when I prepared some of those slides from our earlier pilot study where we kind of had 3-year simulation, then we were eager to see what happens in 2014, and it was like basically summer this year when we started this. Basically, we kind of had a gap, and we just restarted the model at the end of 2013. So basically, we have 3 years. It's like baseline, like weak climatology on that, and it's 2014. So what's shown here is in blue you have surface temperature at number of moorings on mid-shelf, like Oregon Shelf, Monterey Bay, and somewhere in South California Bight. So blue is the data and red is the model, and you kind of see like exactly 10 p.m. on that particular day we hit that particular temperature. Well, the difference is that we don't do it. The model is a bit more diffused, but there is some skill there, so it kind of keeps this red kind of ends up warmer than it was in those colder years. So it does show some skill, and it's same as in South California too. Well, when I saw that thing, the first thing I thought about like this anomalously weak winter, and I would be personally curious to learn more how that would precondition coastal dynamics, if there's effect or maybe upwelling wind, favorable winds just washed it out in summer. So one way to address actually how interior ocean and coastal ocean interact is to look at volume integrated balances, and basically we do it for four different years in this couple of simulations. And this is analysis for the Oregon coast. So basically we're looking at what affects the temperature, volume integrated temperature between 41 and 46 north on the Oregon Shelf, and between coast and 200 meter isobath and from surface to the bottom. So we have this volume average temperature, and two things affected the atmospheric flux, and we kind of integrated, like show the cumulative atmospheric flux and kind of normalize it to make units of temperature. So basically it says like if there were no any exchange with the interior ocean or with boundaries in terms of heat flux, basically in a given year we'll get like between 4 and 6 centigrades in temperature change. And this red line is the 2014. So basically it's kind of, we see like compared to those 3 years, to 9, 10, 11, so this has the largest heat flux locally on a shelf. And that's, heat flux comes from the atmospheric model. That's like 12 kilometer resolution, no-num model. And, but that, we don't boil the ocean, you know that. And so that's because this increase in heat is balanced by the advection of heat out of the domain, which is shown here. So basically until, well, this is year day, so until somewhere in August, we kind of take out as much heat from here as other years, and then kind of this warm blob is coming probably, and you can start exchanging shelf waters with warmer interior ocean waters. So that's kind of my interpretation. South California, we have this spike in temperature, and that's mostly because of the cross-shore, and all the longshore and cross-shore advection through the boundaries of that box. So not as much because of the anomalous heat flux. That's again based on the model. And for kind of for the winter, if you look at the cross section here, kind of we have seen that already. So these top panels, January, February, March, this is n squared, the buoyancy frequency, kind of you see like stronger stratification. Then I just chose that one of the stronger winds, winters 2010, kind of have deeper seasonal thermocline and weaker stratification. And kind of, this is kind of too fresh maybe to really go in every detail, but we're trying to see how this change in stratification affects the vertical turbulence flux. And I should say, well, when you have very deep mixed layer, so sometime like this in April, you have this heating or cooling at the base of the thermocline because of the turbulent processes. And if you look at 2014, when you have a more shallow thermocline, you don't have that process as much, all right? But then, what I didn't show here, but I started kind of looking at temperature and those terms, kind of providing, like making profiles, averaging over this section. Still, like by May, June, something like warm water is coming, despite you don't have a lot of mixing. So like basically you have this increased heat by horizontal advection rather than by vertical flux. Right? So thank you.
Thanks. All right, so that's 3 or 4 things that might be discussed. Uwe, did you want to go next, or? Yeah.
So there's a contribution here?
I've actually just sent the email. Got the first one, okay. The second one should be in a second. Turns out I'm just your grad student. I was actually in a class with Dean Remick spring quarter last year. And we had a discussion about the warm blob, and he actually made up a few pictures with Argo, Argo data, and then hopefully she's pulling them up. We can show the second one while the other one's coming in. That's fine. So this is going to be Argo data taken at a point. It's 145 west, 50 north. And I'm Dylan Amaya, by the way. I'm at Scripps. I'm a second-year PhD student at Scripps. And really just the main thing I want to mention here is that Argo does show, at least in the heart of the blob itself, that it is a shallow anomaly. I mean, it seems to break off here at 100 dbar. The bottom plot is going to be the time series of temperature anomaly relative to the 10-year mean that Argo has in that area. And if did the second one come? I can just show you where it is relative to the full thing. Okay, and it's here. Cool. Okay, so the top plot is going to be Argo surface temperature, anomaly relative to that same 14-year period. And the bottom plot is going to be the top 100 meters integrated. So I just wanted to show you where he put that. I don't have a pointer, but it's at 145.50 north. So it's at that point, somewhere in the center of it. So it is pretty shallow, according to the Argo data. So there you go. I'm sorry? Averaging period is, for this, it's the entire record that he had for 2004 to 2013. And then if you could go to the next slide, please. And then the Hovmuller at the bottom is actually just going to March of 2015. So obviously there's more data to be had there, but, and actually for the last few months, it does show a deepening that I just now noticed to about 250 dbar for what it's worth. But it does seem to be all in the top 100 meters or so.
Andrew.
Hi, I'm Andrew. I'm going to bring us back to 152 West and the P60 North section.
And can you introduce yourself?
Oh, I'm Andrew. I'm a 6th-year graduate student here at the UW and hopefully finishing up soon. So this slide, one day delayed because of this workshop, but you know. So this slide is contributed by my advisor, Sabina Mecking, who is co-chief scientist on P16 North. And so one of the things that we just really wanted to show real quick was differences in oxygen, right? So if you consider oxygen as a tracer of ocean ventilation, one of the things that is a little bit interesting to show is that we might be able to tease out some kind of sign in terms of, or some kind of change between occupations of the cloudbird cruises in the speed up or slow down of the gyre circulation or the oceanic circulation. So in this case here, and I apologize if I get the sign wrong because this is my first time looking at the slide in any close detail, is that on the left-hand panel there is the difference in oxygen between 2006 and 1991 occupation. And you can see that there is a little bit of a negative decrease in oxygen there, right? So that would basically imply a slowdown in circulation. And you can also see that it is also still consistent in between our 2015 and 2006 occupations of the same line, right around 40 north, 45 north, which is kind of the same latitude as the center of the blob again. So, I mean, it is deeper than what was shown, what Dylan just showed. And if you remember my previous plot of the temperature difference, we also showed that those anomalies kind of were maybe stretched around 150 dB, decibar, and 200 decibar. So it's a little bit hard to say, but if you're talking about boundary conditions between the open ocean and coastal ocean, I think one of the really important things to be able to tease out too is what the large-scale transport is actually going to be in this region that might deliver more or less open ocean water to the coast.
All right, yes, over there.
Yeah, Rick Tolman, Weather Service Alaska region. And so we, very nice observation-based anomalies, great. Okay, so what's it look like on the global scale? So this is just a plot from the Climate Prediction Center. I don't think there's any Climate Prediction Center people here, but I just took this off their website. So this is the upper 300-meter heat content from the GODAS analysis. And sure looks like a blob to me. There in the Northeast Pacific, pretty substantial integrated heat anomalies still in the Northeast Pacific, and then certainly higher magnitudes down off of Baja and, of course, El Nino. And notice here, at least in the GODAS analysis, the bottom panel is a change from November, and the stormy weather in the Pacific Northwest here, at least, again, this low-resolution model does not appear to have had that much impact yet. And I got one more there. And just looking at this little box here, Yanhee at CPC, so 40 to 50 north there. And you can see here, again, from GODAS in the recent, this most recent blob. Notice now we do have this anomaly extending much deeper than we've seen in the past since 1979 here. So there you go.
Thank you. All right, anybody else? Yes. Manny?
Can I ask a question / joke? Today, I've seen a lot of pictures where there's a huge blob also in the Gulf Stream. I wonder if that was significant at all. Does anybody know anything about that? Or was it just coincidental?
You know, I've wondered that too, and sometimes people have said, well, it's just a shifting of the location of the meander, and that's what gives you the false signature when you look in anomaly space, but I'm not sure I accept that just because I see it so persistent in various months, and I don't know. I think we need to know more about that, so it is interesting. All right, anybody else, or shall we shift to Uwe to the south? Yes.
Just regarding what you were just saying about the anomalies in the Gulf Stream region, in 2012 we had very strong warm anomalies off the East Coast. I'm Melanie Fewings from the University of Connecticut, and Ketchen at Woods Hole showed that those anomalies like that, but in 2012 were due to changes in atmospheric forcing from a jet stream displacement. And I think he has been working on this more recent anomaly as well. And you should check his recent paper, but I think it was a combination of the change in atmospheric forcing and changes in advection in the Mid-Atlantic Bight.
Sorry, Uwe. And when you talk about heat content, you have to realize there's sort of two parts to it. There's one part is the thermocline heave, which can adjust relatively rapidly and even propagate away as Rossby waves, and the diabatically forced heat content, which is the actual heating of the upper ocean. So as you look around the globe, there's contributions from both of those terms depending on where you look. So you can't just look at that and say you know that it's the same type of thing that we're seeing in the North Pacific, which is clearly diabatically changed in the upper ocean.
All right, Uwe, go.
Okay, I would like to give some in situ views of the conditions and try to shed some light on the processes of Southern California. And I'm going to use mainly in situ observations from the glider and mooring program from the Cork and CCE mooring projects funded by NOAA. And these are the collaborators and people who contributed. So the observations we have, we are collecting routinely are the three glider lines here that Mark Ormond already presented using Catherine's slides, and she has a poster here to write, Catherine, so everybody is invited to see the poster. So I'm starting off with some of those slides again, which frame the large-scale conditions in the region, and then I will try to combine that, in some sense contrast that with mooring observations. And the moorings I'm going to use is the CC2 mooring, which is in the Upwelling region off Point Conception, CC1 mooring, which is in the southward flowing California current core, and this nearshore mooring off Del Mar on the shelf in 100 meters water depth. That's where we have the longest time series. So for the large-scale picture, these are the slides Mark showed. They are really Catherine slides, and I'm sure they are on a poster. Just to summarize again, these are temperature anomalies in the 10 upper 50 meters, essentially, on the three glider lines as a function of distance from the coast and as a function of time. And as Mark pointed out, there's this nearly simultaneous occurrence of warm water beginning of 2014 over a very large region. So these are anomalies. And another slide from Catherine that Mark, I think, showed, which is now a depth section as a function of time averaged over the three glider lines, showing that, again, we have heard this several times, it's a surface intensified phenomenon, not as deep as the typical El Nino signals, restricted to the upper 30 to 50 meters or so. And again, this is averaged over the large region of southern, essentially Cal-Coffee region in some sense. And these are the temperature anomalies averaged over the three glider lines. Each color is one of the glider lines, and I think Mark showed that too. And of course, we see the strong warming in 2014, but depending on when you start doing your trend, you might already see the beginning of a warming in 2012 or 2013. So maybe this is a warming in the anomalies that actually started a bit before 2014 already. And I will show some other evidence that might support that idea. And this is an important result from Catherine that summarizes some of the driving mechanisms. And again, this is closely related to things we have discussed several times already here. These are the surface heat fluxes. The top line shows the net surface heat flux from the NCEP, that's the nowcast model, right? The NAM. And averaged over this large region here. And they're all positive numbers, but you can see unusually high values, higher by 10 to 20 watts per square meter in 2013 and 14 essentially, which is probably related to some of the warming that we see in the region. And also, if you take the NSAP-NAM wind stress data and take the wind stress magnitude, not the direction, not the longshore part, just the total wind stress magnitude, averaged over the whole region, there seems to be a decreasing trend in the wind stress magnitude. So there's some conclusion one can draw from these is that firstly there's anomalous heat input from the atmosphere due to the increased surface heat flux and maybe reduced upwelling if you look over the whole large region here. And now I'm going to switch to more localized views that we get from the mooring observations to try to look at some of these processes in more detail, but only at a few points. That's the caveat, of course. So these are, again, the moorings we have in the water. CC2 is the one that we have most heavily instrumented with physical biogeochemical sensors. And here are some anomaly time series from chlorophyll fluorescence, nitrate concentration, oxygen at 15 meters at this location. And one can very clearly see the anomalies that are related to the warming in 2014 and 15 in all the variables here. I'm just showing this at the moment to maybe help the later discussion about ecosystem impacts and also highlight that we do have very high time resolution to analyze individual events like upwelling events, advective events, and so on, which we can look at with the mooring data. At the mooring, we have longer time series since 2006. This is the upper layer temperature. We see the two previous El Niños here as a weak signal and the big anomaly from the last years. So with this slide here, I want to kind of frame the discussion about the 4 possible mechanisms that can lead to anomalous warming. And the first point I would like to make is the bottom is anomaly. This is what we often look at. And in anomaly, we see the warming starts in 2014. So this is anomalous warming because the anomaly becomes more positive. And maybe the anomalous warming starts a bit earlier. But if you look at the actual temperatures, at that time there was still cooling. It's not surprising. It's similar to the spatial maps of anomaly versus true temperature that we saw this morning. When you look at the true temperature, you don't see much of a blob. Only when you take anomalies, you subtract the typical field, then you see the anomaly. So what's important is this cooling means there was upwelling, because if you just integrate the surface heat fluxes, you would not get this cooling here. So this means that even while this warming happened, there was upwelling activity which cooled the water. And that's not surprising because Mike Cosser already showed us that in this part of the coast, we don't have a switch between upwelling and downwelling. We either have upwelling or we have no upwelling, but we always have some upwelling, which always causes some cooling here. So if we want to now ask what processes could have caused this anomalous warming in the first half of 2014, because that's when it started, and then of course more pronounced later, these are the mechanisms we probably need to look at. So first question is, were there higher surface heat fluxes? And the data I showed earlier from Catherine suggests that. One question is there reduced upwelling, which would mean reduced cooling during this phase, and therefore lower amplitude in the temperature drop here. It could also be advection from offshore, like happens further north of Oregon and Washington, where when the upwelling season stops, you get downwelling, the offshore warm water moves in towards the coast, and that's what causes the warming near the coast. So that's something we can check with our observations. And we can also address with the observations whether there's anomalous advection from the south, because we know to the south there's warmer water. If there's anomalous northward flow, it will bring warmer water and contribute to anomalous warming. And some of these things we can address with the observations that we have. We spent some time trying to convince ourselves that our moorings actually can measure the cross-shelf upwelling circulation. And the first thing, in order to try to do that with good ADCP data, is that you have rotated your currents correctly in the alongshore and cross-shore direction, because otherwise you project alongshore flow into what you think is cross-shore flow. So this is a progressive vector diagram here of, for 1 year at the mooring in the upwelling region of Point Conception. And it's pretty clear which direction is the longshore direction, because this is the poleward flow at the lower layers. These are the layer depths here. And you can also see in the upper layer, first there's offshore flow during the upwelling season, and then there's poleward flow when the relaxation after the upwelling season sets in. So from this, we can pretty well establish the direction of cross-shore and alongshore. And so when we do this rotation, then we can calculate the cross-shelf displacement at this mooring in the upper layer in order to see whether we can observe the upwelling-driven offshore flow at this location. And these are the cumulative displacements in the upper layer in the cross-shelf direction. And so this is negative, means the flow goes offshore all the time, which is consistent with what we know now, that the wind is always upwelling favorable in Southern California. So when it becomes more negative, means the flow goes offshore. There is some break in the slope here. So until middle of the year, it goes a lot offshore, and then sometimes it stops. There are slight onshore wiggles, but it doesn't really go all the way onshore again. And this is the end of the upwelling season. This is kind of where it breaks. It stops from going offshore to more poleward. So we can see the overall behavior that we expect from the wind observations. There's offshore flow for half the year, and when the upwelling season stops, it kind of just becomes more poleward. The thing to note is that 2014, which is the purple curve here, shows upwelling offshore flow the whole time. So which means that there is no onshore displacement, which could lead to the warming that we observed here. So 2014 had more or less continuous offshore flow, meaning upwelling the whole time. And we can do similar things at the Del Mar mooring, which I'm not going to show in the interest of time. So then we tried to convince ourselves that the signal really is the upwelling circulation. So we looked at the vertical shear, and these are the time average vertical shears from January to October for different years, and 2014 is the orange one. And we see here, this is rotated in a funny way. This at the surface, this is offshore, and this one is onshore flow. So this is the typical circulation in the cross-shelf direction you would expect from upwelling, meaning the offshore circulation here, onshore here. And if we believe that the shear is a measure for the intensity of the upwelling circulation, we can plot a time series of this, and that is the red curve here. And if we overlay that with the long shelf wind stress, 2 degrees to the south, because we think the wind a little bit further to the south drives the upwelling at this location, then we see a pretty good correlation between the longshore wind stress further to the south, flip the sign to make them have the same sign, and shear, which we think, therefore, is a good measure of the upwelling circulation. So we think we can directly observe the intensity of the active upwelling circulation with these moorings. And these is the average over 2014. And you can see 2014 actually has pretty large shear on average compared to other years. So we think that this implies that 2014 actually had normal, maybe even strong upwelling circulation. We also looked at wind stress data, and we used the NCEP reanalysis model to see whether there were changes in the upwelling strength as a function of time, as a function of location. And we took the long shelf wind stress anomaly at 1 degree distance from the coast, and then went along the coast from 22 degrees to 40 degrees. And this is a function of time. This is wind stress, poleward wind stress anomaly. So negative means more upwelling, positive means less upwelling. And in 2014, if we average over this, we actually on average have more upwelling. This is as averaged over the first half of 2014, the second half of 2014, compared to 2013. as a function of latitude, and the Southern California Bight, where our observations take place, are in the shaded box here. And you can see that there is definitely no indication of weaker upwelling winds in this location near the coast. So at least this reanalysis model suggests that there is not anomalously low upwelling in 2014 in our part of the region. And when we compare it to an NEBC buoy just south of Point Conception, that's actually confirmed. The long shelf upwelling forcing winds at this NEBC buoy in 2014 are the same strength as in other year and shows the same seasonal cycle. So I know this is somewhat in contrast to other observations that we have heard, and therefore I hope that will lead to some discussions. A few slides about the poleward flow. We heard a lot already today about a long shelf advection from the south. And these are now, again, progressive vector diagram, the same progressive vector diagram, but now we analyze the displacement in the alongshore direction. And this is the cumulative poleward flow, again in the upper layer. And the years 2013, 14, and 15, those are the three colors here, have much larger northward poleward flow than the other years. So we think there's an indication of a lot more flow of warm water from the south into the region northward along the coast. And we can try to find this in the water mass properties, and this is a north-south water mass index. It's very similar to spiciness. We took a box here in the north and a box in the south and looked at the properties in the TS space, and then we took a TS measurement on our moorings and calculated along isopycnals whether it's closer to this or closer to this, and then we gave it a weight. When it's red, it looks like this. When it's blue, it looks like this. And so red means that the water is more likely from southern origin, and these are now the water mass indicators at the three moorings, Del Mar, CC1, CC2, and one can see a dominance of red colors in 2012 and 13, even at the offshore mooring here, and also at Del Mar, which is consistent with this enhanced poleward flow that we observed in our mooring data.
Can I ask a question?
Yeah.
Can offshore water...
Can you use the microphone?
In your previous diagram, can offshore water also impact this index, or is it just north-south?
It can. We would have to look at water mass properties more offshore, and I think that's maybe related to the question about the zooplankton species we heard earlier, because the statement was that those zooplankton species that were anomalously observed in the region either must have come from further south tropics or further offshore. So the same argument can apply here, I think. Yeah. Satellite images also suggest that already at the beginning of 2014 there was anomalous northward advection from the south. So this is the more typical situation at the beginning of the year, January 2013, January 2014. These are SST images from Mati Karu at Scripps, show an intrusion of warmer water northward along the coast, which again is consistent with those direct observations that we have. And it's also consistent, I think, with state estimates from the Cork team at Scripps here. They have calculated a longshore flow indices all the way from Baja California to Point Conception, and this is the time series of Baja California. To look, eyeball a bit, zero line is here, so positive means poleward. And even though the time average may be close to zero, there are 6 month periods with strong enough poleward flow. If you multiply this, this is strong enough over 3 or 4 months to reach Point Conception. So I think these poleward flow events are strong enough and long enough, even off Baja California, to transport water all the way to the north, and that's also suggestive of satellite images like this, which show the warm wedge of water going towards the coast. And we have to always remember the mean gradients are always such that warmer water is in the south, so if you have northward flow, it does have a warming influence and brings a warm anomaly. So this is my last slide, hopefully leading into discussion. So to to recap, the data that we have analyzed show that the upwelling itself, the direction, the offshore upwelling, seems to continue also during the anomalous warming phase. So we do not have, like of Oregon, the onshore flow of warm water. It also looks like the upwelling circulation was not anomalously weak in 2014. The longshore advection from the south shows that in the previous years, already 2012, 2013, but also continuing in 2014, must bring warm water advecting along the coast from the south. And this then creates different initial conditions at the upwelling season, for example, for 2014. The ISO pigments are depressed, the nutrient values are low because of this anomalous advection of water from the south. So what causes the warming then is probably, to a large extent, the surface heat flux. And in fact, for the more offshore large-scale data that Catherine has analyzed with a glider, I think that's the only mechanism that's left that would make sense, I think. But there's a problem a little bit if you look at the different models. So Catherine used the NSAP-NAM, the nowcast model, and her time series is the black line here. So that's net surface heat flux over the different years, and these are the high heat fluxes I showed earlier. If you take a different NSAP model, the NSAP North Atlantic Region Reanalysis model, depending on where you do this analysis, you get the different colors, but none of them show anomalously high fluxes in 2013-14. So there are differences between the models. Based on results, I'm more inclined to use the one Catherine used because it's more consistent with the warming that we observe. But we had some slides today from NSAP models, so maybe we can discuss more about the different models and strengths and weaknesses and so on. And the other question, I think, is the poleward flow that clearly exists and must bring a lot of warm water into the region. It probably affects the biology. I know Mark has observed species from the south. We heard earlier today already the zooplankton species that must have come from far away somehow. What forced these northward flows? Did they propagate into the region? Were there sea level signals that propagated from the south? We already saw the analysis by Ted Strupp this morning. There doesn't seem to be a coherent signal propagating all the way from the equator into this region in sea level, or both analyzing sea level data and tide gauge data and altimetry data. So I think that's also an open question to address. Maybe there are people in the audience who have insight data, model results, and so on, that have an explanation what might have caused the northward flow in the region starting in 2012, roughly.
Okay, thank you, Uwe. So who has something they would like to contribute? Well, I do. If nobody's going to take the bait, I'm going to let people think about it a little bit more. Rachel, could you cue up? Yes. Okay, so my question is about upwelling, and Julie Keister showed this slide earlier. And so the point being made was that 2014, if you look back at the months where there was typical upwelling, the water near the coast was either normal or a little bit cooler than normal. And then when we transitioned from upwelling to downwelling, everything was much warmer than normal. When we looked in 2015, we really didn't see that pattern so much. It was red right up to the coast. And if we go to the next one, this is a slide she didn't show. So when I first saw this pattern, I thought, well, it's probably because upwelling was different in the two seasons. But this is the smooth daily upwelling index at 48 degrees north. Here is March through December of 2014. Here is January through December of 2015. And you can see the zero line here. So I just put stars there if it was upwelling. And they're blue if it's cooler than normal water temperatures at the coast, and they're red if it was warmer than normal. And so 2015 did have upwelling, and in fact, even a little bit longer of a season than in 2014. But what is interesting to me is that the waters near the coastline in, I think this is July and August of 2015, were warmer than normal. So my question to the physical oceanographers is that the source waters that are being upwelled were just anomalously warm and influenced by the blob, or is there some other dynamic? Yes. Sure. So, all right, so Francis is adding something to that while you guys gin up an answer for me.
So I'm Francis Wilkerson. The other thought is when things are warmer in upwelling, it's to do with relaxation and the extent of the relaxation phase. And everyone's pointing to upwelling, but no one's talking about the relaxation window. So I'm just throwing that in as another warming explanation.
Right.
So how does the relaxation change? And is the warming because of the warm water, or is it actually because it's staying up there for longer to warm?
I mean, the seasonal trend, the end of the upwelling season is also, it's like a relaxation because the winds weaken and you get the northward flow, and that's just like a classical short relaxation after an upwelling event. And so probably if one wants to look at the full time history, the sequence of upwelling relaxation can contribute to the warming because it's a kind of a rectifying process, and we probably could do that with the mooring data. We haven't looked at that, so that's an interesting potential process to look at. I suspect it would work in the opposite sense here, because if you have a lot of upwelling, intense upwelling events, you get a lot of strong relaxations, which might actually bring you more warm water into the region than having overall weaker activity. There were other...
So your interpretation of the red stars is?
Well, firstly, I'm in some sense pleased to see that because it's consistent with everything that Mike has shown, that I have also analyzed and so on, that the wind forcing and probably the intensity of the upwelling circulation doesn't seem to have been weaker in 2014 and 2015.
Right.
So it must be either different source water, but then where do the source waters come from? And probably it must be an advective effect. So it would be interesting to look at the data of Oregon, to what extent there is northward flow during some season and some year, or during strong relaxations also in that part of the coast. So we are only familiar with California, but the data exists, so I'm sure somebody has the answer for that.
Thank you. All right. Yes.
So I can add to that off of Oregon. I'm Jennifer Fisher. I work at Oregon State University. So we have a time series of temperature and salinity that I'd like to show you. And just to reiterate what Mike said, is that we did see variable upwelling along the coast latitudinally. And so to put this into context, again, this is only for Oregon, but with the temperature and salinity signal, we actually saw that on the shelf, we did see anomalously warm and quite fresh water, but the source waters were not anomalous. So hopefully you'll be able to see that. And just to kind of recap a slide that Julie showed this morning, from the back-end index, if you look at the cumulative upwelling, 2015 was the strongest cumulative upwelling that we saw in a 20-year time series. So Julie showed this morning, but just quickly, that teal line, 2015, all the gray lines are the past 20 years of cumulative upwelling. And at 45 degrees north, we actually saw the strongest cumulative upwelling. But despite that, So this is, the top plot is temperature and the bottom is salinity from 1997 to just last week. And you see a really strong signal. So this is at a station 5 miles off the coast at the bottom depth, so 50 meters. So in 97, 98, that signal was very warm and slightly fresh. And then you see beginning in 2014, we see it quite warm, quite fresh. And then when that blob came ashore in the fall of 2014, it's incredibly warm. But because of that strong upwelling, which mainly occurred in Oregon in June, we actually do see a slight negative temperature and positive salinity signal. So kind of to get at what you were talking about, Jan, there was enough upwelling to kind of overcome and bring some of that cold, nutrient-rich water up to the coast. But as soon as that relaxed, basically that warm water that was basically sitting off the shelf just moved right back on shore. So one more. And this is kind of the same plot, but one more. But now we're looking 25 miles off the coast at 150 meters. And this is kind of what we use as a proxy for the California undercurrent. And the striking difference here is 97, 98, we had really fresh water in the deep source waters, whereas it's only slightly warm and fresh in this past event. So this might get the kind of source waters. We don't believe that they were anomalously different compared to the 97, 98 event.
Thank you, Jennifer. Yes, please, Ted. Go ahead, and then John, too. The pointer, yes, it's right here. It is that green button there? Yep.
Yeah, Ted Strube from Oregon State. Since this has been showed, I thought I might as well give my interpretation. So, can you go 2 slides forward? So what we do is we look at the altimeter data along the actual lines where the altimeter is collecting the data, and we're looking at the 100 kilometers right next to the coast. There's actually little red lines, and you can see that you can call that coastal because you can hardly see the red lines. So if you go back to, so this is 97, 98. It's been shown already, but we'll just go over it. People have talked about the summer period. The El Nino in 97, 98, and these 2 years, I think of it as having 2 periods. One is starts in May, and at the equator, the first pulse of high sea level arrives about that time. There's kind of a relaxation, and then there's another pulse around November. So you can see that in the 97, 98. We've put the same shading for 2014, 15. Okay, so you can see the latitudes. This is just, this is the northern part of Baja. This is below the tip of Baja. And my point is that during this first period, during the May through August period, actually starting in April, there was a high sea level event in 2014 that could be seen all the way up to the tip of Baja and then maybe slightly up Baja. There was even a second event that, again, didn't really penetrate past Baja California. And it's hard, I'm not really even going to talk about the 2015. Because of the lingering high sea levels, it's really hard to see that as events, although if you look at these low latitudes below the tip of Baja, it does look like more of the typical pattern, like the 2 periods that we saw, except in 97, 98, they propagated all the way up into Oregon. If you go to the next slide. So we've talked about the velocities. What we've done is take the 100 kilometers next to the coast height, subtract the next 100 kilometers, so we have a geostrophic velocity going across the tracks. Okay, in 97, these were very strong during both of those pulses, and they extended up into the Oregon region. Again, they were there during the first pulse in 2014, so Uwe showed the poleward flow, and I would say that it was extending all the way down to Central America and coming up. I think you can still ask the question, what was the dynamics driving it? But it was there, and there was a continuous flow. And it doesn't look like pulses as you go further north, but in 2014, it does seem to have had some connection. The part that doesn't show as coherent a pattern occurs in 2015 until we get into the November period. I'll also point out that the lines here are the north-south wind stress. Okay, so you can look at them and see that, whether or not there were strong wind stresses. And when you get up into the Central California and Oregon areas, in 1997, the high sea levels were carried a lot by the wind stress that occurred in the winter, in the fall winter, okay? We really haven't had that. These are anomalies of the north-south wind stress, and we've only had a few periods with high wind stresses. And the sea levels, or the velocities next to the coast, don't look like the velocities we saw there. So that's my story for that.
Respond to that is that we did very similar analyses looking for the propagating signals, and we also found that there is no coherent propagation neither in SSH nor in the velocity beyond like the southern tip of Baja California. That's where it seems to disappear. But quite apart from that, this April 2014 is when this equatorial anomaly hits the coast of South America and starts propagating north. But the anomalous warming started earlier. The anomalous warming started at the beginning of 2014, months before this. And the anomalous poleward flow we observed already a year before. So I think it's something different. And maybe we can figure it out by tomorrow if somebody has the data set with them. So.
Great, thank you. Okay, one more, John, before we break.
Thanks, Jan. I'm John Lodger. I'm from University of California, Davis. I don't have any slides. I haven't done any analyses, but the picture we're seeing in central northern California is last week of June 2014, we switched out of a normal upwelling situation into anomalously warm water. And it stayed around until probably March 2015, by which time we went back to normal upwelling. So April, May 2015 looked just like any other year. And then the last week of June 2015, we suddenly switched back into anomalously warm, 4 degrees warmer than normal. So it's almost like two states. Because if you go to late 2014 or late 2015, the winds are not really anomalous. The winds have similar strength as any late summer or fall, and the events are just as strong as during the spring season. But probably there's just too much warm water around to push it offshore, too deep, just not enough energy, except for September 2015 when for a couple of weeks the wind blew persistently, probably kind of pushed that water back, and we almost went back to upwelling for a while. So I think the water is, and then on the radar data, the poleward flows, there's no real strong signal of poleward flow, but there's it seems to be a shut-off in equatorward flow again in about June 2014. My sense, and there's no analysis, so I've got nothing to show, is that it's coming from offshore. The warm water is coming from offshore, which will give you some poleward flow as it hits the coast. So we're trying to look at the radar data from Conception up to Bodega, even Oregon, to see is there any sense of a poleward advection. So I don't think there is, but as you said, we still got tomorrow. So
this is the signal you are just describing. After July, north of Point Conception, this is where you are.
Yeah.
There's a very sudden shut-off of the upwelling vein.
So it'd be nice.
Relaxation. So this is this negative anomaly here that we also saw in the data, and that's a very strong relaxation event, which I would be surprised if it wasn't associated with poleward flows.
Well, we should look at it because in the buoy data, we do not see that. The wind doesn't. There's no anomalous drop-off in winds in the fall. So we should look at what's going into that analysis and maybe look at some other buoys as well. Yeah, I wanted to ask you about that. I thought I'd color you afterwards. So at particularly the buoy off Bodega, which I know the best, there's no drop-off like that. So the local winds, but it's very shelf data. So lots to talk about.
Great, thank you. Oh, one more comment. Come on up.
So I'm Ann Hollywood, and I don't have a comment, I have a question. I'm on the biology side, and I asked this of Nick yesterday, and maybe you can help me. from our side, we would like to know whether or not the events that we've seen over from Washington, Oregon, California, Canada, Gulf of Alaska, represent something like what we might see under global warming. And what you're telling me is that this is a complicated event, and I'm wondering, what's your take on it? Can we think about it that way, or should we just say this was a unique event and it really isn't a good harbinger of climate change?
But to the extent that much of the forcing probably is atmospherically driven by these large-scale Taylor connection patterns, I don't think we can answer that with local observation. This is more, I think, a question for the previous discussion group, and there are experts in the room for that. But the one thing I would dare to guess is, even under global warming scenarios, there will always be the large north-south temperature gradient along the coast. If you go south, the water gets warmer, it's very clear. And I also think that we will continue in the global warming scenarios to have a sequence of upwelling and relaxation events. And so when you have relaxation events in our part of the coast, I'm very sure you will get poleward flow of warm water. What triggers anomalously warm flow and what triggers the anomalous heat fluxes, this is something we are trying to find out, and I don't think we'll know how that will change under global warming.
I'm a physical oceanographer and climate dynamicist. I'm not a biologist. And I like to work with biologists, and sort of the typical thing that I like to focus on is how does the physical climate variability and the physical ocean variability affect the ecosystem. And the typical way you do that is you measure over a long period of time the jiggles of the physical system and measure the wiggles in the biology and try to relate those two things together in some typically linear fashion. So in the 2013, 2014, 2015 period, we had these extreme anomalies in the ocean. I mean, sometimes 4 standard deviations off the mean. So as a physical scientist who likes to work with biologists, I would say, if you really understand your biology, you must be able to know what would happen to your particular system under those conditions. The changes in the physical ocean were not just a local extreme event. These are changes that occurred over thousands of kilometers of scale. Basically, in the upper 100 meters of the water column, everything got really warm for a really long period of time, months and months and months at a time. So this, I would imagine that this is unprecedented. Of course, we could look back at other types of historical records and try to see if it was. We could look at global climate model runs to see whether the global climate models can ever produce such a persistent, large-scale extreme event in the ocean like did occur in nature. I don't know whether anybody has tried to do that yet. But we could basically look at this now, and each of us who measures biology would have their particular spot, and biologists tend to be very fine scale. I think we'd like in this discussion to be more broad scale and focus on mechanisms, and we want people to come up and say, you know, how did your biology respond to these extreme events? What is the mechanism that actually caused that? Explain it to us. We could also think about what measurements should we have made in order to understand things better, and also what things we want to do to sort of synthesize our results and all work together to try to understand things better. The question was raised by Ann Hollowed, is this what global warming might look like? I think that if you 15, 20 years ago, looking at your climate models, you'd see this thick mat of warm water in the North Pacific that looks very similar to what happened. So this could be a analog of what to expect in the future in terms of the physical climate state. Hence, if the biology is responding strongly to this, that might be a good look at what biology of the future might look like as well. And to distinguish this from El Nino, at least along the California coast, I would say that during El Nino events, the thermocline tends to be depressed with surface warming, whereas in this situation, the thermocline is relatively flat, but there's still this mat of warm water over large scales over the whole Northeast Pacific. So that, I think that's sort of the difference in prototype or, of what this physical anomaly is like. So again, we will be, after Bill gives his little spiel, we will invite you up to say what mechanism affected your biological variable, what else do we need to do to understand it, and what might we try to do in terms of measuring things in a little bit of a different way in the future.
So before you do that, I really want to reiterate, the microphones are critical, and we've been thinking, oh, this is a bother, it's only for the people watching the live feed, and I bet they're not even watching it right now. But guess what? In the back of the room, you can't hear. And several people told me this at the break, so please, please, please use the microphone. Don't go like this and then come back, because they can't hear that intermediate part. So please, everybody, really use the microphone so that all of us can participate equally. Thank you.
I have a question about your comment about the global warming. If it is a global warming, should we also think about expecting like cold blob? I mean, you know, if it's such an extreme event that you produce warm event from the atmosphere, could it be also the reverse at some point that we have like a huge cool event?
First, don't misquote me. I didn't say this was global warming. I said this is what, if you had looked in climate models in the North Pacific, 10, 15 years, probably now as well, you see this surface warming that leads to enhanced stratification, right? In reality, of course, there's a lot of different things that go on in global warming, including changes in teleconnection patterns, dynamic responses that I'm not talking about, just talking about for the simplest way we thought of the ocean under global warming would be enhanced stratification with basically a warmer upper ocean and not much else happening underneath. Let's put it that way, sort of the stagnant 1D model of global warming. But you're right, there's all kinds of other things that could happen due to dynamic effects associated with it, and in fact, could lead to cold areas as well, right?
Thanks, Art. Yes, this is the Art and Bill show. I'm Bill Seidman. I'm from the Farallon Institute in Northern California. And as Art mentioned, we were tasked with speaking about the ecosystem perspectives and mechanisms of ecosystem response, or facilitating that discussion. And I don't have data slides. You'll be happy about that. But I do have a few word slides to go over. So first of all, bringing us back to the blob and what Steve McQueen was saying way back when. And even though Nick tried to take over this, I think Steve is still the master. So he called it indescribable. It's not really indescribable. In fact, we've done a very good job at describing it so far. So McQueen et al., they were incorrect, basically, or sort of. So we've seen lots of patterns, and we've seen these patterns through the day today with lots of the talks that have been presented. But we still don't really have all the pathways of biotic responses worked out. And of course, that's really very important for the social and economic issues and conservation issues that people are concerned about. So we still have a lot of work to do, but I think that's okay. It's still early, and we're working on that. So, and then the question about, is the blob indestructible? And this, Mike McFadden talked a little bit about this morning. So what's the forecast for that? So the early El Nino indications are that the blob, is being overshadowed by El Nino, but really only time will tell. And if La Nina comes after El Nino, which it often does, then that may lead to a reestablishment of the ridiculously resilient ridge, and then a blob formation again, so forth and so on. So I think that we really have some number of things to consider yet. So being a little more serious about things, let's see. What do we know about mechanisms of ecosystem response so far? This is kind of my take. I was pulling this together during the earlier sessions this afternoon. I think the number one thing that I have gotten out of all of the talks so far is that we're really seeing this substantial regional variability in both physical and biological responses. For example, we've seen sort of lesser effects, if you will, in the California current due to the upwelling system. versus what's been happening in the Gulf of Alaska and up into the eastern Bering Sea. We've also seen really strong seasonal effects. It looks like fall and winter responses are clearer, but I'm not quite sure about that. But that, again, is just an impression that I had. The physical drivers of note so far, again, at least to me, the 2014 El Niñito, for lack of another way of saying it, off Baja and the Southern California current system. I think just because it doesn't make a 5-month threshold or the 5 to 7 month threshold, that doesn't mean that something doesn't happen. And certainly there were strong ecosystem responses to whatever happened early in 2014 as well. So we shouldn't ignore that. It was a start and stop event, but it was part of this overall system. Keeping the blob at bay, certainly that's one way of describing what was going on in the central part of the California current system through the upwelling. As long as the upwelling system was functioning seasonally, it seemed like the blob was kept offshore. When it ended normally towards the end of the summer or early fall, depending on where you are in the system, the blob and its impacts were felt in the ecosystem. Now we have the 2015-2016 El Nino. We're seeing sort of some of the traditional reduced upwelling. Other sort of typical or usual preconceived mechanisms seem to be in place, but not everywhere. So that's something else that we need to consider, that there are these mechanisms that are happening, but some of them are again, providing surprises to us. In the Gulf of Alaska and further north, I'm really confused about this. It seems like people talked about enhanced upwelling, enhanced mixing, but also reduced mixing. I don't understand this, so if somebody can come up and explain this, that would be really great, because I'm not sure we understand what's going on there. Overall, I think that from a biotic standpoint, what we need to focus on is this spatial variability or regional variability that we've seen throughout the system, and then also how it impacts food web dynamics. So what are we trying to understand in terms of biotic effects so far? There are a number of big things that have gone on, but at least to me, the whale and bird die-offs that we've seen at the upper trophic levels are really a big story. And they're ongoing, particularly in Alaska now. There's a huge die-off of common murres. It's another species of seabird. They're very severe. We're talking about hundreds of thousands of birds that have died at different trophic levels. So at first it was kind of a zooplanktivorous bird. Now there's piscivorous birds that are being affected. And then we had planktivorous whales and other whales that have died. We're also trying to understand the variation in production at different trophic levels. So kind of fundamental questions, if you will. I think the approach, I see this as a major opportunity that we have right now. I put natural experiment in quotes there because how can you have an experiment if it's naturally occurring? But it's really a natural experiment of a no analog system. We've never seen anything like this before in the North Pacific, and looking at it with effects at all these different ecosystems, but each ecosystem is responding slightly differently. So that's that spatial variability again. So I don't think we have any really clear answers in terms of these mechanisms yet. We have lots of different ideas, but we need to put them together. But I think that the opportunity is to make spatial comparisons of these mechanisms in the different ecosystems. And that may be particularly useful to developing greater understanding. Some things to consider, some mechanisms. The conventional thought here would be that the responses that we've seen across trophic levels are forced by bottom-up mechanisms. Again, this is kind of the conventional upproach, if you will, the NPZ to fish, bird, mammal approach. And we understand, or we think that upper trophic levels are controlled by lower trophic levels. So if that's true, we should be able to explain the observations that we see by standard relationships between temperature variation and primary productivity. Something got missed there, from phytoplankton to zooplankton and so forth up the food chain, or up the food web. But there are other potential mechanisms that we need to consider, top-down mechanisms. For example, with these changes in water masses that we're seeing in different regions, there usually are associated redistributions of predators, and so there could be control mechanisms from the top of the food web as well. Another thing to consider, there have been a lot of nasty phytoplankton out there, domoic acid, PSP poisoning, things like that. They could be explaining some of these things that we're seeing as well. So there are a lot of different mechanisms. We shouldn't just focus on bottom up, although that, of course, is a great place to start. And that's all I really have to say. You know, here are the three different sort of things that we had: the blob up to the north, and then the El Nino in the Baja region, and then the full El Nino down south, and the upwelling system. So that's all I really wanted to say. And Art.
So one of the, I'm going to first of all mention something that came out of the last workshop, and then I'm going to pose a question to Bill, who should not leave. So from the last workshop, a picture was emerging of, at least in the southern, or along the California coast, of an explanation for a lot of strandings of California sea lions, pups that were emaciated, suggesting that the mothers weren't giving enough milk because they weren't eating enough sardine. And I think there was also an idea that the sardines were also being reduced. And I presume that that has been potentially linked to reduction in productivity through these, the increased stratification and the bottom-up effect. So that seemed like a nice picture that it was at least being painted at the time. If there's someone in the audience who has more to say about that, I would really like to hear that. That's what I was hoping someone would now get up and run here in queue, because next question I want to ask Bill, you mentioned two things, the whale die-off and the seabird die-off. Have those been conclusively linked to not enough forage, that they were, emaciated whales and emaciated birds, or might there have been other processes that cause those types of die-offs?
Yeah, that's a good question. And I think that, no, they haven't been conclusively linked to changes in food yet, but hopefully we will have some people come up and talk about that. Where is Tim? I'm just going to call you up here, so I know you've got it, so.
There is a line of people.
So, oh, sorry.
So I'm Melissa Carter. I'm at Scripps Institution of Oceanography. Since we're asking about the bottom-up portion, what we're looking at, or the data that I'm going to be showing you, is from the SCOOS HAB monitoring. As part of that, because we're scientists and we can't help but to collect more data than just what we're supposed to be collecting, we're also interested in understanding the phytoplankton community. So there's 5 stations that are collected along the coast. Scripps Pier has been a long-term site that's had data that's been collected since 1916 at various different times because of programs and funding. What I want to show here, and again, one of the things that we've talked about today, is that how different the system has been throughout Baja all the way up to Alaska. And so for Southern California, we've seen actually something very different. Mark Oman showed this with Manu's results of the surface chlorophyll. So we have seen a major decrease here. The stations going from south to north. And trying to create a synthesis figure, you're going to lose a lot of detailed information. I just want to throw that out there. So if we look at a 5-year mean, these programs started in 2008. You'll see that we have fairly consistent chlorophyll concentration throughout the bight. As you get into central California coast, we have higher chlorophyll, as you would expect, increased standard upwelling that happens. And then whenever I presented some of this data before at the first workshop, we had seen a decrease in the phytoplankton concentration starting in November of 2013. The samples that were coming in, the reports that were coming throughout California, we weren't seeing anything. And it was really striking to me that all of a sudden we have diversity, we have organisms that are in the water, we see nothing. And so that was really brought to my attention. So originally I'd worked this up using that as the date, but I had changed just to this warm period of 2014 to 2015. 15, and you can see there's a drastic change in the amount of chlorophyll. We also count the total number of cells when that's available, and you can see that there's a very similar decrease. Some of the stations do have changes in variability, and I'll try to add some more figures tomorrow to my poster that might be able to help provide a little bit more synthesis information about this. As to the cause, I'm not sure. There's so many different ideas. But again, we've seen the warming, I think, is really important here. And the one question that I want to throw out is, at least for us, recirculating this, or an idea that Bill Peterson threw out there was that copepods and drifters have to come from different source water. And for us, we're not seeing anything. So are the copepods eating what was potentially there, or is it the same water that's just sitting around and then just being upwelled again? So throwing out more questions, why not?
It's Ann Holloway again, and this is just a shout out for our poster over there. Ross Hopcroft this morning showed a figure, but you asked about seabird diets, and of course, H1 pollock in the Gulf of Alaska are a real prey, and the 2014 year class looks like it was just gone from as of using an H1 index from the 2015 acoustic survey. So that is just a heads up that we're working on the fish side, so obviously we'd like to reach out to you guys.
Hi, I'm Jennifer Jackson from the Hakai Institute in Canada. And one thing that I think needs to be mentioned is the long-term shoaling of the surface mixed layer at Ocean Station Papa. Data have been collected there since about the 1950s, and the trend, I believe, is about 56 meters per century of the maximum winter surface mixed layer depth. And so I think what this could imply is that there's a long-term trend of surface mixed layer shoaling, and perhaps this blob is just an extreme on that trend. But long-term, it does suggest that the blob is something that could happen again and again in the future as the surface mixed layer continues to shoal.
Hi, Mark Oman again. I have a comment that's not directly relevant to this session, then one that is. The comment that pertains to the two previous sessions is I keep hearing people refer to the upwelling show, the upwelling variation was the upwelling anomalies were. Remember, the Bakken index is an index. At the very best, it's, well, what it is, it's based on an atmospheric pressure gradient. At best, it's an index of wind. That's not going to necessarily tell you how much nitrate is being transported upward from below. You have to know the in situ water column structure. You have to know the nitrocline depth. Is the nitrate available to be transported upward by the action of the wind, or is it way down deep? So just keep in mind, although the index is useful and practical, it's not telling us what we really want to know. End of lecture. The point I wanted to make here with respect to mechanisms is, and you've alluded to most of these, Bill, is I think it's useful to think of a suite of mechanisms and to be a little agnostic at the beginning as to what the operative mechanisms are. Certainly there is in situ local heating effects on stratification and nutrient supply. Those local effects that we think of as propagating from the bottom up. Those are food web processes. Also, there is lateral advection, and there's lateral advection on small scales and then large scale geographic displacements. I think that's a second very important category. There's also the altered either availability or activity of predators. And actually, we might include parasites, predators and parasites together in that concept. And then finally, there is the direct physiological responses to increased or decreased temperatures. The physiological responses of organisms and upregulation and downregulation of genes in response to these physiological stressors. So those are 4 mechanisms. There are papers that delineate these. I think those might be useful to, I would suggest keeping all 4 of those mechanisms in mind before prejudging the outcome of a particular study.
Is this one on? Here we go, yeah. So Mark is the head of the LTER, Long-Term Ecological Research, California Current Ecosystems site, and I'm actually part of that too. And these guys go out on cruises. I don't, I just do models, but these guys go out on cruises. In the summer of 2014, right, they went out there to study the fronts of the California current in the southern, off of Point Conception. And instead of finding any fronts at all, they just were in this soup of warm water. So if your organism or your part of the ecosystem relies on frontal dynamics to be, continued, then these types of situations might be very detrimental to that part of the ecosystem. So is that a fair assessment?
That's very fair, and that was my first awareness of the effect of large-scale anomalies in the Northeast Pacific. And at that time, this is August 2014, I kept looking to the equator. What's the source of the equatorial forcing that would have led to these mid-latitude anomalies off the coast of California? The projected El Nino of 2014, quote, didn't happen, but of course Ted has pointed out to us that in many respects it did happen. And what I didn't know at the time was I should be looking much further to the north, and Nick Bond helped stretch my thinking much further to the north. The cruise that we had in August 2014 was intended to focus on the hypothesis that mesoscale and submesoscale fronts disproportionately shape nutrient fluxes and predator-prey interactions in the California current system. We had to scrub the plan completely because there essentially were no fronts. There were not strong horizontal gradients. So the ocean forcing really changed our circumstances. The cruise immediately preceding ours was Ken Brulin from UC Santa Cruz, who was interested in iron fluxes in strong upwelling regions where there is a precipitous decline in bathymetry and no continental shelf sediments to shed iron to fertilize the system, in contrast to strong upwelling in regions where there is a shallow shelf and potential iron sources there. He was intending to do his work off the Big Sur coast, off Central California, but had to take the ship further and further and further north, eventually getting up to Oregon before he finally found strong upwelling influences. So it was a dramatic forcing event that affected a lot of the coastal ocean.
Thanks, Mark.
Hi, I'm Tim, and I'm a postdoc with the Coastal Observation and Seabird Survey team. And we work with a team of volunteers who collect data on beach bird observations along the west coast of the US. And just as a brief introduction, from October 2014 through to February 2015, there were unprecedented numbers of Cassin's auklets, which are a small diving bird that feed predominantly on copepods and small crustaceans. There were unprecedented numbers of these birds found on beaches right the way through from California all the way up to Washington. And at least from the mechanistic standpoint, at least the understanding at the moment is that these birds were compressed into a narrow band in the nearshore environment where there was still cold water habitat, for want of a better word, for these species. And so you start off with a lot of these birds in the very close to the shore. And then as the blob went from offshore and moved inshore, you then get a change in both the food composition and also the food quality. And so you get a shift from the cold water copepods to the predominantly warm water copepods, which means that these birds are unable to forage as effectively. And so all of a sudden you've got a lot of birds in the nearshore environment that are dying, but also because they're so much closer to shore than they would be usually, you then have an increase in the deposition rate of those birds as well. And so there's both an increase in mortality, but also an increase in the perceived mortality of these birds simply because they were much closer to shore than would be expected. And so that's part of our understanding at the moment. But there was also some aspect of the breeding colony, and we know that the year leading up to this seabird wreck was that there was a particularly good year on the breeding colony for these birds. And so there was potentially more juvenile individuals in the water at that time. And so you might even expect an increase in mortality just because of the number of juveniles there as well. And so that's kind of our thinking at the moment around the Castins Auklet wreck. And yeah, I'm presenting a poster over there, so if you've got any questions, just feel free to come over. Thank you.
Hi, I'm Dr. Terry Rolls with NOAA, and I run the Marine Mammal Unusual Mortality Event Program for NOAA and U.S. Fish and Wildlife. Yeah. And so I've heard a lot of references to marine mammal deaths, and somebody presented this morning about the large whale UME in the Gulf of Alaska, and we have a meeting next week on bringing all the data together for the Gulf of Alaska mortality events. But I just wanted to go through the odorite mortalities off the coast of Baja and California. And so there's been mention of California sea lion deaths, and looking at the long-term series, you can see that strandings of live 0 to 2-year-old sea lions, so animals less than 2. This doesn't take into account the UMEs associated with domoic acid, which are 2-year-old usually and to adult. Started in 2013, went down in 2014, and then 2015 was a bumper year. This is not all mortality. These are animals that were reported live, handled by the rehab facilities, and either died or lived. And so this is not the total aspect of what's going on. And this only for 2015 only goes through November. We don't have December numbers yet. Then Guadalupe fur seals, again, if you look at Guadalupe fur seals stranding in California, it's again anomalous as far as the number of animals stranding. And you can see what the peak months are, April, May, and June, and most of those also are emaciated or starvation. And then the next one. And then northern fur seals. And you can again see how anomalous the mortalities are for northern fur seals going back as far as 1992. Northern fur seals, this is just the data from one of our rehabilitation centers in Central and Northern California. We don't have all the data pulled together yet for 2015, and this is going on into the beginning of 2016. And again, these animals are very thin and emaciated. There are a lot of other underlying things going on because as you starve to death, a lot of other things start to happen. But what we're doing right now is our Alaska Fisheries Science Center and Southwest Fisheries Science Center are going to the rookeries in the next couple of weeks to evaluate what's happening on San Miguel and San Nicolas. We also are working with Guadalupe, which is where your Guadalupe fur seals give birth, and we're evaluating what's happening on these rookeries, what's happening with the pups there, and that will determine the information we get from that will probably tell us whether it's going to be a bad stranding year, i.e. the people along the coast see stranded animals. And if they see the stranded animals, that means they lived long enough to get in their starvation state to the coast, or they've died on the coast, and it'll look like a really good year along the coast, but it won't be a really good year for sea lions. So a lot of information, we can go into a lot more details. I'm a wildlife veterinarian, and I'm trying to learn oceanography and climate and weather and all of these things, but I want to make sure that you understand what's going on with the mortalities. We also have had anomalous mortality events over the last 3 years in Chile, Peru, and Central America. So I think there's a signal across the Pacific, not just in the North Pacific. Thank you.
I want to make a potentially ignorant comment that the warm anomalies have persisted for more than 2 years, and it looks like the real killer was the second year, so that perhaps the animals could be resilient to one bad year, but if you start stacking them up, that things could get precipitously worse.
Hi, I'm Sonia Batten. I'm from British Columbia working with the Continuous Plankton Recorder Survey. And what I have here is continuous survey, but I've focused on two areas, the Alaska Shelf region and then the Oceanic region off of British Columbia. And what we found is that in the last couple of years, we're looking at the diatoms in our samples, and the proportion of the cell types that are long and thin are much higher, much more abundant than usual, whereas the more centric diatoms are much lower in abundance. And I've got, for each of those two regions, I've got the proportion of the cell types. So it's just off the right-hand side of the screen here, but in 2015, these are spring data, spring 2015 in the offshore region, for the first time ever, more than 50% of the diatom community was comprised of these longer, thin cells. Now, these cells have a higher surface area to volume ratio, which means that nutrients can diffuse in much more easily, and that gives them an advantage in low nutrient conditions. So if you're asking for a mechanism, then I think that the reduced mixing and perhaps reduced advection, especially in the offshore region, is encouraged to lower nutrient surface waters. And Jennifer mentioned the Station P data. Certainly in 2014, they had low surface nutrient measurements. So I think that that favors this type of diatom community more. Now, completely speculative, if they have a higher surface area to volume ratio, then they're going to have more cell wall structure made of silica to kind of tasty, nutrient-rich cell interior to feed the higher trophic levels. So perhaps this is one way that a change at the bottom of the food chain could impact higher trophic levels. I also have a poster with some of the zooplankton changes that we found, but I'm going to let Russ, because there's a big lineup, talk about zooplankton, and I have a poster.
Thank you.
Okay, I'm Russ Hopcroft. I'm from the University of Alaska, and I maintain the long-term monitoring line south of Anchorage. And if you can put the slide up. So this is one of our bread and butter players. There's 3 species of this group called Neocalnus, and they just chalk up lipids over the course of the year. This is what sustains their egg production the next year. This is what sustains their ability to go down and hibernate in the winter. And a lot of animals are really dependent on getting this big food-rich, high lipid value food. When we went out there in the spring of last year, we had very variable status of the lipid accumulation in the animals across the line. And that's not unusual depending on the year. The expectation is they're eventually going to finish loading up with the lipids they need, and they're going to go down to depth and sleep. As Mark said, when you have a project targeting an animal and you go out, you usually find it won't be there. So at the end of the line in September, we went out, we tried to go down 600 meters and capture these animals, which are supposed to be at depth, sleeping, loaded up, rich in lipids. And what we found was we weren't finding animals in good condition on those hulls. In fact, we had a lot of dead carcasses, we had a lot of dead animals, and we had animals that really weren't very rich in lipids. Of course, because we were doing it for something else, it was like we threw everything away because it wasn't going to work, and then after the fact we go, should have saved them, because then we'd have quantitative information. But what I want to make the point is, come to the next slide. So this is the way that energy is partitioned in an organism. We get energy coming in, and that goes off to respiration, and it goes into growth, and in the case of Neocalnus, it goes into storage. If we've had bad years, intense stratification, less nutrients getting up, there's going to be less phytoplankton available to support the animals. And what you eat, more of it's going to go down that chain that says respiration, less of it's going to be available to go into the thing that says lipid storage. So I think what we're looking at is we're looking at the stratification has decreased the overall food availability of the animals. They've been less successful in accumulating what they need in the way of lipids to go down and do their diapause. And this may be responsible for some of the other crashes we're seeing permeating through the food web, where a rich food source that the organisms are expecting to get just wasn't there in 15, the second year of having to deal with these challenges, and that may be responsible for some of the cascades we're seeing in the ecosystem.
Thank you.
I'm John Payne. I just have a ignorant question about 2 mechanisms that I haven't heard anybody talk about today, but I've heard about them in other conferences. One of them is a shallowing of the low oxygen layer, which essentially squeezes available fish habitat. I'm wondering whether that was a factor this time. And the other is ocean acidification. I've seen charts showing that it was relatively strong along the coast, and I'm wondering whether there's any interaction between the climate changes we've seen with the blob.
Maybe someone could comment on that straight away, or since it's a direct question.
Hi, good afternoon. I'm Simone Allen, and I'm here at NOAA's Pacific Marine Environmental Lab, and I was kind of at the back of the line because I wanted to make the point that in the middle of this year, a number of us around this area did kind of a mid-year assessment of the effects of the blob on local ocean conditions and ecosystem impacts. And it occurred to me at that time, looking at the data up to July for this year, that we were sort of looking at a future experiment analog of temperature only, right? And so in the future, we can expect to see the impacts of not just the changed temperature on all the organisms we've been hearing about, but also the added couple hundred ppm of PCO2 that we can expect. And so kind of to answer the question that was raised, I think Julie Keister showed the slide of what was going on with oxygen in Hood Canal earlier this year, and we did see very low, close to anoxic levels of oxygen, and based on an estimate using oxygen and temp as proxies for aragonite saturation and so forth, we also saw the lowest aragonite saturations and pH values that we've seen. It wasn't a direct measurement, but confidence is pretty high that that's the case. So while we couldn't necessarily decouple the environmental or the ecosystem effects of CO2 from those of oxygen and temperature, they would certainly have their effects on the sensitive organisms to those parameters. So certainly interlinked phenomena, but not with the added burden of a few hundred extra ppm in the atmosphere. So.
I'm Andrew again from the University of Washington. This time I'm going to pose a question, which is maybe perhaps from a physical perspective, is that to me that there seems to be two different phenomena that kind of make the blob a pretty unique kind of unique phenomenon, which is one is the magnitude of the temperature anomaly, right? That it is these 4 degrees C anomalies, and the other one is the persistence of it. So I was just kind of curious to know, for the people who have observed impacts or changes in the ecosystems of whatever biological biome that you're looking at, can you speculate as to whether the effect of the blob on these things is due more to just the pulse of a really quick, hard stressor on it, or is it the integrated effect? So is the response that you're seeing a delay from just an impulse, or kind of a integrated response?
Hi, Jennifer Fisher again, Oregon State University. We have a 20-year time series from zooplankton abundance off of the Oregon coast, and we've been able to observe the implications of the warm and the cold water copepods to the effects of 7 different El Nino events. And we see a really strongly and positive relationship with both the magnitude of the event and the duration. So both the magnitude of the El Nino event and the duration is really strongly linked to how long it takes for those communities to respond or come back to normal. So this could be pretty bad, actually.
Hey everybody, my name's Tom Bell, and I'm a graduate student at UC Santa Barbara, and I study giant kelp from both laboratory and remote sensing techniques. I have a poster back there if you want to talk to me more later. So giant kelp is right on the coast. It's usually pretty shallow, in the upper 30 meters. And we have seen in the Santa Barbara Channel massive declines of giant kelp canopy and total giant kelp biomass over the past 2 years or so, leading to a complete absence right now, most likely due to the El Nino. So what I've been doing is looking at the chlorophyll to carbon ratio of the canopy kelp blades, kind of like a proxy for physiological state. And we've seen that the chlorophyll to carbon ratio has been decreasing over the past over 2013 or 2014 and 2015. And we think that it's related to the growth rate of the giant kelp. And it has to continuously put out new fronds to maintain a canopy. And what we've seen through hyperspectral remote sensing is this decrease in the chlorophyll-carbon ratio throughout the channel and actually throughout the state of California. And we think that's kind of related to this decrease over 2 years, kind of a step-down decrease. We had a really good year in 2013, about half decrease in 2014 during what we call the blob or warm event in Southern California, to a complete loss in 2015. And again, I have a poster if you want to talk more about it. Thanks.
Could I ask a follow-up question, since I don't really understand how kelp grow? So they need the sunlight and they need the nutrient. How do they get the nutrient? I mean, obviously they get the sunlight by growing way up near the...
They sit
but
right
how do
at
they get the nutrient?
Well, presumably through upwelling events.
No, I mean, if
Oh,
they're...
it's direct?
For instance, the water column would have a lot of nitrate at depth, but not very much at the surface because it's already consumed, right? So they're putting their fronds out where there's light, but there's not much nutrient up there. So they have to
but they attach down to the bottom.
So they suck it up near the bottom? Is that how they get the nutrient?
Presumably, yeah. So we've actually seen we have some hyperspectral images from AVERIS, which is an aerial imaging spectrometer. And we've seen that the chlorophyll to carbon ratio of the canopy is related to the depth of the reef. So deeper plants tend to have a better physiological state at the canopy. So presumably they're taking up more nutrients at depth and translocating that nitrate to produce more chlorophyll pigment at the canopy.
Hi, my name is Stephanie Zador, and I work at the Alaska Fisheries Science Center. I wanted to show a data-free slide here, but what I do is I develop, curate, and monitor ecosystem indicators to put in an annual ecosystem status report for Alaska, and the report is for the North Pacific Fisheries Management Council. And what I wanted to highlight was the difference in the ecosystem response between the two warm years. So in 2014, we saw a lot of big shifts in the physical indicators that we monitor. This includes the PDO, the North Pacific Gyre oscillation. We saw big changes in things such as the cold pool area in the Bering Sea and our water temperature, surface temperatures during our surveys. So these were really a big shift from the previous sequence of cold years that we had. And then our biological indicators were mostly positive or showing high productivity, things like groundfish conditions. So this is length weight residuals in the surveys. The groundfish were heavier per length than on average. And seabirds had extremely high productivity both in the eastern Bering Sea and the Gulf of Alaska. But in 2015, what was interesting is that those physical indicators that we monitor remained the same. You know, there weren't big shifts, and even including things such as the PAPA trajectory index, which is the surface current, the simulated surface current drifter that's released from Ocean Station PAPA, was very similar in 2015 to 2014, and that's unusual in the time series. So we had this continuation of warm, but in contrast, most of our biological indicators that we monitor showed low to average to low productivity. So some of these data sets have been reported on already by other people, but there were things such as, let me see, I have to remember now. Starting with the lower trophic. So we had mostly small copepods in our surveys, and this is what we'd expect in warm conditions and tends to shift the food web to a less productive state. We also had very few H0 pollock that were found, the lowest on record in the Gulf of Alaska. We had poor groundfish conditions, so during our surveys they were much lighter on average per length than usual. And then the seabirds did very poorly this year, and of course we also had a lot of anecdotal observations of the dead birds, and of course the whale mortalities, et cetera. And so I just thought this was interesting, and one potential mechanism or some point that I wanted to bring up that I think Art alluded to before was that sequence matters. We had had a series of cold years and then the switch to warm, and so I think there are some carryover effects when these sequences differ. So one example, and this is speculative, but something like a themisto, which is a large Arctic amphipod, can build up. They live multiple years, and they can build up in sequential cold conditions, and then when there's a switch, there's a difference in the food web that maybe some of our predators can take advantage of. But when those warm conditions persist, we're then shifting back into what's a more typical low productivity system. And there's some evidence that we saw this in 2003 as well, which was a warm year after a cold year, but just didn't have the exact same length sequence. So I just wanted to make that point that I think carryover effects are important. And then also with these indicators, you know, response time varies. We see things like changes in range distributions pretty quickly in response to warm water events, but then some of these other indicators we monitor are probably going to take some time to show impacts, depending on how that is promulgated through the food web. So that's all.
Thank you.
Hi, I'm Andy Lysing. I'm at the Southwest Fisheries Science Center. The last 2 years, I've actually been in charge of putting together the Cal Coffee State of the California Current Report. So what I've done here is actually give a kind of summary from the last 3 years. Is there a pointer, or can I take this with me closer to the board? Oh, okay, I can do this. Okay, so this is 2013, 2014, 2015. I apologize, I went around the back. I know the people in the back probably can't see the words. What I did was I overlaid some words on here saying what was doing well and what wasn't doing well from these reports. And in the back is just chlorophyll A. And so actually there was an earlier question about, do we have to worry about a cold pool? I think Manu asked it even. I would argue that in some ways, 2013, when that report was being put together, we were actually worried that that could almost be like a cold pool. It was one of the record years of upwelling index, Mark. And actually the result was that from north of Point Conception, where the upwelling index actually does a pretty good job of predicting temperatures and productivity, there actually was very high productivity. Everything that was coastally upwelling related did really well in 2013. In fact, the end of that report, people were writing that they were concerned that it would be so much upwelling that year that it would push the biomass offshore. You wouldn't get an accumulation of things for all the other trophic levels to eat. That turned out not to be the case. Okay, then we go to 2014. You'll notice most of the words here, if you can't even see what the words say, but the words disappeared because the species all disappeared and did very poorly in 2014. Something that was very interesting, though, was that we still had these pockets of upwelling, which you can see actually in chlorophyll, high little pockets of chlorophyll here due to upwelling in little patches. And so there was still some coastally associated species that did well, like rockfish. There was still some euphausias around. Down in the southern region, though, in the Cal Coffee region, we went from having relatively high zooplankton, decent primary production, down to poor numbers for that. And again, people asked earlier about sardines and anchovies. They've actually been gone from this area down here since about, I think it's 2010. They've been gone, but their numbers are decreasing and decreasing. All that was left was mackerel. And then we switch to 2015. So the overall gestalt from this report from 2015 was that wherever people looked at species composition, they saw this really high species richness because they were still getting the coastal species because there were still these pockets of significant upwelling. And so still the rockfish larvae did fine in Central California. But only a little ways offshore from that, you had these warm blob waters. So in some of their same exact trawls, they were catching coastally upwelling related species and species they would often see during El Nino and new species they'd never seen before that was presumably these offshore species coming in. So I think that just points to in the future when we're thinking about these events and you're trying to monitor it, if you just look at one species and say, oh, the abundance is going up and down, that's maybe not going to tell you the whole story. It's really this idea of community shifts that we saw. And I think that was the overall gestalt from this last year, was that there was just a change in the overall community that we saw all up and down the coast. And this was also an interesting year in 2015. Finally, we saw sardine and anchovy. They weren't down here where they were supposed to be. They're all way up here in the north. Okay, so we finally had sardine and anchovy. So it's almost like the things that could move, not plankton, but fish and other things, may have all moved north. The stuff that has to stick where it is, it's the things that do poorly depending, or they might do okay if there was a pocket of production where they were. So I guess another thing too is when we're worried about the blob, It's not just that the blob is out here and it happens. It's that for our coastal species and stuff we're trying to manage in the near shore, we need to worry about whether that blob gets close enough or even comes right into the shore to change our community composition. So we need to worry about not just the strength and where and the blob, how long it is, but if it can get to the coast and impact.
So the wrestling match is not Blob versus El Nino, it's a tag team match. Blob and El Nino versus the fish and birds.
Yeah, I just want to make a comment too. Hang on one sec. If you want to ask a question, you should get up too. Andy, I think that was a great summary. It's exactly the kind of temporal and spatial comparison and synthesis that we need for the entire North Pacific region to try to understand what's going on with the communities. So thank you for that.
So looking at this map, if I understand correctly, these patches of chlorophyll are somehow an indication of the net productivity of the upwelling cells along the coast. Is that fair?
The biological oceanographer in me says no, because biomass is not primary production.
Okay.
The practical fisheries scientist in me says yeah. So.
Well answered.
He's a very careful man. So the question now is, it is really patchy. And we are talking about these large-scale coherent events. And I presume that if you were to look at the upwelling indices that Mark brought up, they would be pretty coherent along the coast. But yet, at the coastal response, it's really different. And so I'm wondering whether the ecosystem response at this level, you know, when we look at species and trying to assess this community thing, whether we can actually talk about large-scale coherent events along, you know, the North American coast, or if we're just doomed. Because I don't even understand, you know, how you get these kind of coastal patches in terms of the response here.
Okay. Actually, it's not, Manu, actually, there is some coherence in the upwelling index, but it's not as coherent as you would think as you get closer to the shore. And actually, the patterns in 2014 and 2015, where there was patches of chlorophyll, actually do match pretty well with that, if we look at the upwelling index right in that nearest location, yeah. So it's not as incoherent as you want, or I mean, it's not as coherent all the way up and down the coast as you might think. So yeah, we can actually narrow in on in 2015 this area, and you can see that it was actually still anomalously high upwelling there and pretty much at those spots, yeah. Sorry.
Biology.
I'm Alfonso Hernandez from a Mexican NGO named Grupo de Ecología y Conservación de Islas. And I'm just want to tell you a bit about our observations on seabirds during the last two years. So we detect a decrease in the total numbers of nests for 2014, and we saw an even lower number on the total nest for 2015. But we also saw massive abandonments of nests for the first year, for 2014, and an even higher number of massive abandonments for 2015. And we also saw low chlorophyll levels and high sea surface temperature, as you have seen during all these presentations. And so we are now thinking about all of these possible relations with the physical and biotic variables. And we are open to any ideas, and we bring a poster about that. Thank you.
Could I ask a follow-up question to that? When you think about birds nesting, sometimes they nest, but the eggs don't hatch and they don't get more birds from the eggs, but sometimes they just don't bother to nest at all. Are those two different things that are thought of in different ways as to what controls that type of behavior or success? Did I phrase that slow enough?
Yeah, so we saw many birds that actually arrive to the islands and they lay eggs, they build their nest, lay eggs, but then at some point during the season they abandon, and in big numbers, thousands of them, they just left the islands. The eggs were there, and sometimes the chicks were there, and they just just were.
But
just
sometimes do they just not even show up at all, or do they always show up? And
No.
sometimes they leave in the middle of trying to hatch eggs.
sometimes they just don't show up as, for example, in Ras Island, I think there was a slide during the earlier presentation. So it's a very important nesting site for seabirds in Mexico, in the Gulf of Mexico. Thousands of birds, breeds, nest there every year, but during the last 2 years, there has been a very, very low number of birds that arrive there. And in Mexico, what we have seen, I mean, in the other part of the Baja California Peninsula on the Pacific, we have seen low numbers of the total nest. I mean, there are low numbers of birds arriving to build their nest, but also once they build it, lay eggs, some of them just leave the nest because, we don't know, perhaps difficulties on find their prey availability or prey abundance. We are still trying to figure it out.
Okay.
Thank you.
Thank you.
So Ted Strube from Oregon State. I just wanted to misquote Art and to raise a question. I thought you said that the blob meant that water properties changed along isopycnals, but you didn't move the isopycnals up and down. And El Nino meant the isopycnals moved up and down. So what I thought I heard for Southern California is that the water properties did not change along the isopycnals, but they were depressed. And what I think would be useful is just to answer those very specific questions in each of the regions. When did you see properties change along isopycnals, and when did you see the isopycnals go up and down?
Toby Garfield with the Southwest Fisheries Science Center, and actually with Chris Harvey, one of our responsibilities is the California Current Integrated Ecosystem Assessment, where we have to give a report to the Pacific Fishery Management Council. And I think one thing that has been left out of here is what's happening on land, on the land side, how that is implicating the coastal ocean, and in particular the storage of water. So this are 3 images, 2013, 14, and 15, of the snow in the mountains. And what you see is that in 2015 there was almost no snow. And if I can have the next slide. The snow water equivalent is a measure of the storage of water, which is really important for the spring and summertime discharge of water. And judging by the plot here on the left-hand side, in almost every one of these basins, the snow water equivalent was down to about 5% in 2015. It was at 30% in 2014. So the landward side of this whole thing really needs to be looked at as well. Thank you.
And it's obligatory that we have to at least mention salmon at one point during
Exactly.
this.
Yeah. Think of the poor salmon who, first of all, are having trouble in the rivers, and then you saw what the conditions are like when they get into the coastal ocean. They don't have a prayer.
I was also going to use salmon as an example. My name's Olaf Wormseth. I'm a fishery biologist with the NOAA's Alaska Fisheries Science Center. And I don't have any slides, but I wanted to just offer some, I guess, food for thought that's come out of a bunch of, I've been involved in a lot of this type of work, trying to integrate physical environment and biological responses. And I guess another title for this would also be sort of why people get frustrated with biologists. And the first part was kind of getting back to something I think, Art, you said about we tend to look at things at a very small scale. And that's definitely true, but if you're looking at a biological or physiological response, you really have to begin there at the physiological level. So kind of my first point was that, particularly looking at the blob, that responses, if you look at fish anyway, that responses are probably going to be really acute. And this gets at this question of global warming and the relevance of the blob to global warming, that I think the blob might be analogous to some aspects of what we might see. And so some of the responses might be a good example. But in general, you're going to see both between acclimation and actual adaptation, you can really see some fundamental change in biological organisms over a longer period of time that you're not going to see, even with a 2-year blob, you're not going to see that kind of fundamental change that almost certainly will occur over a longer period of time. The other aspect of acute responses is really in terms of perception, and this is something I always have to remind myself, if you're, especially if you're a very small fish, your ability to both perceive the environment and particularly to perceive your immediate environment, to perceive alternatives to your environment, and then your ability to do something about it can all be, insurmountable challenges. So if you're a hake in British Columbia, you don't know that it's cooler up in Alaska. And so kind of how fish respond, this is one reason why yesterday we were having a meeting and we were talking about, well, a more immediate response is probably a fish going deeper, because that's something they can immediately do. They can seek out, find an alternative. There's colder water down there. If that's what they want to do, it's right there. And that's a much different kind of response than a geographic shift. And then my, second point, which is also kind of related and another source of frustration for people from biologists, is that a lot of times we say, well, it depends. But there's a really good reason that we say that, and that's that, especially for something like a fish, which is cold-blooded and is really kind of at the mercy of its environment, every choice basically involves trade-offs. So and I guess the first part of it is that first depends on what you're trying to do. So if you're a age 0 fish, you're trying to maximize growth, get big, survive. If you're a salmon returning to a spawning stream, you have to maximize your both your energy accumulation and then minimize your energy expenditure, which is why salmon won't go into streams until they're cold enough, or they won't go in if they're too warm during a warm year. So it really depends on what you're trying to do as an organism. And then on the flip side, there's a number of things that will influence that, whether it's energy accumulation or whatever. So 4 simple things would be temperature, food availability, the abundance of competitors. And so this is why in fisheries, one of the big things we look at is changes in population size and density, because that can have a huge impact on your sort of decision-making as a fish. And then the 4th one would be predators. And so any fish is trying to sort of optimize all 4 of those at the same time. And so that's why it gets really complicated. And sometimes sometimes it's simple. Like again, salmon not wanting to enter a warm river. Sometimes it's very simple. But for a lot of marine organisms, a lot of times it's a very complicated response and usually involves a number of different factors. And I guess that's what I had to say.
Thank you.
So I'm Chris Holdreed. I'm with the NOAA Bay Laboratory up in Alaska, and I'm also part of the Gulf Watch Alaska Ecosystem Monitoring Program. And I'm a physical oceanographer with a question from my biological colleague, similar to what Anne asked earlier of us. And this is the question about, the community shifts. And one, I'm saying, okay, we've had a big change. Stephanie was mentioning this from a period, at least in our part of the North Pacific, of quite cooler temperatures to a big ramp up to warm. It's a fast transition, so it's a big perturbation. So the response of that in terms of a shift, not just variability from 1 or 2 years, but actually changing the system. In some sense it's thoughts on that, but in some sense it's a challenge of, is there anyone in any of these different parts of the system willing to make a prediction about whether we think we've gotten enough of a perturbation to make a shift rather than just, an up and down change. And I think I told Olaf that I was going to ask him that question, or Bill, or Anne, or Stephanie. If you think like we're in that place, or what do you think, what's your timeline on when we might be able to say that? How long? He said, yeah, it's not 2 years. But okay, for the 76, 77 regime shift, it was 10 years, right? Before we kind of said, yeah, we've seen this. And that was a really big change. So anyway, just thoughts on that. This is probably fodder for discussion tomorrow. But if anyone's willing to make a prediction, I think I might be willing to buy them a beverage.
That's easy.
Thank you. It will change. Anybody else?
I'm Kirsten Lindquist, and I'm with the Beach Watch program, which is a effort-based bird and mammal program at Gulf of the Farallones, Greater Farallones, actually, National Marine Sanctuary. And one piece, we have a poster, actually, our data is included in a couple posters in Tim's, Cass, and Zocklet poster, and then we have another looking at our 3 unprecedentedly huge mortality events since November of 2014. And I just want to point out one piece. It's important to know how many birds or mammals are washing ashore to try and characterize the event. You really need to know what the age class is. You know, if these are really long-lived species, some of these individuals will experience several El Niños in their lifetime. And so having many failed breeding years is no big deal. But we have some age data for these mortality events on our poster, and we have looking at several months of the common murre mortality event for this, just actually this fall. And looking at that over just 3 months, you see a major shift from mostly hatch year, very young birds dying to a much larger percent being adults. And so that looking at those breeding age individuals and the impact to them is going to give us a better sense of the overall impact to the population.
Thank you. Anybody else?
Hi, I'm Steve Fred. I'm Steve Fredkin from Olympic National Park, and I just wanted to comment briefly on sea star wasting disease and the relationship between sea star wasting disease potentially with the blob, and particularly with anomalies. Last week, we had a summit in Seattle on sea star wasting disease and some of the causes and effects of it, and I presented some data there from some of our long-term monitoring data on the outer Olympic coast. And one of the interesting things about that is that particularly sea star wasting disease, by the way, is something that is affecting now over 22 species of sea stars, both subtidally and intertidally, and it is affecting organisms from basically Alaska down to Baja, California. And it has persisted now since 2013, so it's quite a big event. On the outer Olympic coast, what we are seeing is that the incidence of sea star wasting disease appears to be related to warm water temperature anomalies. So whenever the temperature anomaly is 1.5 degrees or greater, we see a spike in sea star wasting disease. And this is in the intertidal zone with the sea star Pisaster ocratius, which is the original keystone predator. So, yeah. And so in particular, in the winter of 2014 and 2015, we've seen our highest incidence of sea star wasting disease, about 60% of the population, and that has corresponded with about a 2-degree temperature anomaly throughout the entire winter there, which is consistent with some of the data that a variety of folks showed today. So I just wanted to speak for the sea stars.
Okay, thank you very much. Is there anybody else? Okay, well, I'd like to, Dr. Peterson. Grandpa.
Oh, I do? Okay. Light. My name's Bill, and I haven't had a drink in months. Anyhow, but what I wanted to add is something we haven't mentioned today, and that's that the persistence of this warm problem is going to continue, probably for maybe a lot longer, and that's what frightens me. It's not so much the big problems we've had last year and this year, but if this goes on one more year, we're going to have a lot of dead salmon on the beach, a lot of dead sea lions, a lot of dead fur seals, a lot of dead auklets, murres. I mean, it's going to be a nightmare. And I lose sleep over this. And that's my big thing.
So we have to pray for La Nina.
Pray for. All right. Thanks, Bill. Is there anybody else who'd like to make comments? If not, I would like to thank all the speakers who came up and made our job so easy for us. I have to stand off to the side and